Hi, this is Stu Schwartz from MasterMathMentor.com. This is video Precalc 03A, and the topic is right angle trigonometry. In the last video, we spent a great deal of time learning the definitions of trig functions and finding the trig functions of both quadrant and special angles. But what about all the other angles? In order to understand how to do this, and more importantly, why we do it, we will introduce a concept called the unit circle. The unit circle, as shown, is a circle whose radius is 1. On this unit circle, we will draw an angle theta in the first quadrant. It could be drawn anywhere, we just choose to use the first quadrant. Now, let's suppose that theta is 40 degrees. So when we find the sine of 40 degrees, we know that it would be defined as y over 1, and that is y. So when we take the sine of 40 degrees, we are really finding the height of the triangle in a unit circle. And the same argument holds when we take the cosine of 40 degrees. We are actually finding x over 1, which is x, and that is the x variable, or the base, in the unit circle. Finally, when we take the tangent of 40 degrees, we are finding the ratio of y to x in a unit circle. So, how do we find trig functions of angles that are not friendly angles? In the past, tables of trig functions were printed in the back of students' trig books. It gave all 6 trig functions of angles from 0 degrees to 90 degrees. This one breaks it down to the nearest minute. These tables were printed in little books and students carried them around. In the mid-1970s, scientific calculators became affordable, and these table of values were no longer needed. Calculators can find values of trig functions to extreme accuracy. The first part of this video is using your TI calculators to find the value of trig functions. Depending upon the types of problems you're facing, you need to decide whether the angles you will be working with are mostly in degrees or radians. In this unit, most of the time angles are given in degrees, so you will use your mode button on the calculator to change the input to degrees. This means that when angles are input to the calculator, they are in degrees. And when angles are actually found by the calculator, they will be measured in degrees. So on your calculator, using the mode button, make sure you are in degree mode and set your calculator to float. That will give the maximum amount of accuracy. Then press the sign button. When you press the sign button, notice that you get a left parentheses with it. Type in 40. You do not have to close the parentheses. And when you do, you will get the value 0.6427876097. That represents the sine of 40 degrees to 10 decimal place accuracy. And remember, what it is that you are finding is the height of this right triangle as shown in the picture. When you press the cosine and 40, you will then get 0.766 with more decimal places. This represents the x value in your triangle. So when you press sine of 40 squared plus cosine of 40 squared, notice that you get exactly 1. This is true because of the Pythagorean theorem. Note that we have to close the parentheses, and we have to use a double parentheses now to isolate the sine 40 to square it, and the cosine 40 to square it. So let's find the trig functions of some angles. Start with the sine of 29 degrees. Punch that into your calculator and you should get 0.4848. Try the cosine of 131 degrees. You should get negative 0.6561. This makes sense because 131 degrees is in the second quadrant and the cosine function is negative in the second quadrant. Problem C shows the danger you can get into when using the calculator. Typing in tangent of 7 pi over 8 will give 0.0480. But since there are no units given, 7 pi over 8 we know is in radians. But the calculator is in degree mode. And the value of 7 pi over 8 is about 2.75 degrees. So the calculator is really finding the tangent of 2.75 degrees. If we want the tangent of 7 pi over 8 radians, we need to temporarily switch the calculator to radian mode and retype it, and we get negative 0.4142. This makes sense as 7 pi over 8 is in the second quadrant and tangent is negative in the second quadrant. If you want to take the tangent of 7 pi over 8 radians, but do not want to take the time to switch back to radian mode, you can do this while in degree mode. You use the second angle menu and use option 3, which is for radians. So we type in tangent of parentheses 7 pi over 8 end parentheses radians, and we will get negative 0.4142 as shown on the screen. But this brings up an important point. You will believe what the calculator tells you. You will rarely question it. And if you do not use the calculator correctly, you can use incorrect information. So it is vital you understand exactly how the calculator works in determining trig functions. Angles with greater precision are assumed to be in decimal degrees unless otherwise stated. So tangent of 12.8 degrees is 0.2272. Sine of negative 0.32.35 degrees is negative 0.5351. Note how we use parentheses around the negative 32.35 to make it clear. And the cosine of 0.724 degrees is 0.9999. We have seen that using radians is a bit messy and perhaps seems unnatural. You might be confused on why they are so important. While a full explanation will make more sense later in the course, let's try to understand why radians are so essential. Suppose you were asked to square your age. We would expect an answer to be between 0 and 100 squared, which is 10,000, because we assume that the age is measured in years. Since everyone on Earth measures age in years, which is one full revolution of the Earth about the Sun, it isn't important to specify units. But if the question was asked to a Martian, the answer might not have the same meaning, as an Earth year and a Mars year measure different amounts of time. The same cannot be true if you are asked to square your height. Two people the same height will give two different answers if they are American and British. Americans will probably measure height in feet, while British will use meters. So the units matter. Suppose we're asked to find the sine of 25. We have seen that angles can be measured in degrees, radians, or revolutions. Math is a universal language. While height can be measured in different units based upon location, it is important that everyone on Earth interpret sine of 25 in exactly the same way. So you might agree with this, but that doesn't explain why we say that no units on an angle signals radians, and why radians are so important. A problem that calculus students see all the time is to find the ratio of the sine of an angle to the angle itself as the angle gets close to 0. So mathematically, we are being asked to find the value of sine theta over theta as theta gets close to 0. Now, let's suppose that theta is measured in degrees. We are looking at sine of 70 degrees over 70 degrees, or sine of 40 degrees over 40 degrees, or sine of 10 degrees over 10 degrees. What do these mean? They have no meaning. The sine of 70 degrees is a number. How do you divide a number by 70 degrees? It is like taking the number 5 and dividing it by $10. You could take $10 and divide it by 5, but 5 over $10 has no meaning. So representing theta as an angle in degrees is meaningless. However, consider the unit circle as shown on the screen. We know that sine theta is opposite over hypotenuse, which is y over 1, which represents the length of y. Now, if theta is measured in radians, then we know that the arc length s is equal to theta r, but that's equal to theta times 1, which is equal to theta. So s and theta are the same. So, in reality, sine theta over theta is simply the length of y over the length of the arc. Now the problem makes some sense, as sine theta over theta is simply looking at the length of the y value divided by the length of the arc. So when theta is equal to 70 degrees, we are looking at the length of y, which is in blue, over the length of arc, which is in green. And that will equal the sine of 70 degrees over the length of the arc, which is 70 degrees, times 2 pi over 360 degrees, as we must be in radians. Note that we don't have to change the 70 degrees upstairs to radians because we are simply taking the sine of it. Whether we change it to radians or not, the sine of 70 degrees is equal to sine of 70 degrees in radians. So when we do the calculation, we end up getting the ratio of the sine theta to theta is 0.769. When theta is equal to 40 degrees, the picture shows that the ratio of the length of y to the length of the arc is closer to 1. And when we do the sine 40 over 40 degrees in radians, we end up getting 0.921. When theta is 10 degrees, notice that the length of y in blue and the length of arc in green are almost the same. So when we do the calculation sine of 10 degrees over 10 degrees in radians, we end up getting 0.995. Luckily, in this course, most of the problems we encounter will use degrees, so it is pretty safe to put your calculator in degree mode. It isn't until we get into calculus that we will find that we have to, most of the time, work in radians. Sometimes you are asked to find trig functions of angles in degrees, minutes, seconds. For instance, cosine of 38 degrees 40 minutes, and 29 seconds. You need to use the second angle menu to input degrees and minutes. So you type in cosine 38 second angle 1, 40 second angle 2, and to get seconds, you use alpha plus, and you should get 0.7807. So finding the value of these three trig functions, you should find that the sine of 82 degrees, 12 minutes is 0.9907. The cosine of 126 degrees, 42 minutes, 53 seconds is negative 0.5978. And the tangent of negative 8 degrees, 57 minutes, 16 seconds is negative 0.1576. Remember that you need to use the negative sign at the bottom of the calculator rather than the minus sign. Note that there are no keys for the cosecant, secant, or cotangent functions on your calculator. No calculator has them. We can find them easily because we use the fact that the sine and cosecant functions are reciprocals of each other, as are the cosine and secant functions and the tangent and cotangent functions. So there are three ways to find, for example, the cosecant of 37 degrees. First, we could take the sine of 37 degrees and then take its reciprocal. Or we can simply find 1 divided by the sine of 37 degrees. And we see these on the screen to the right. You could also find the sine of 37 degrees and then press the reciprocal key, x to the negative 1, and get the same result. Here are 6 problems to try. When doing them, always remember the range of the trig functions. Remember that the secant function and cosecant function will always have values greater than or equal to 1 or less than or equal to negative 1, while the cotangent function can have any value. To find the cosecant of 81 degrees, we take the sine of 81 degrees and then take its reciprocal, and we get 1.0125. To take the secant of 122 degrees, we take the cosine of 122 degrees and then take the reciprocal, and we get negative 1.8871. To take the cotangent of 34.2 degrees, we take the tangent of 34.2 degrees and then take its reciprocal and get 1.4715. To take the secant of 338.292 degrees, we take the cosine of 338.292 and then take its reciprocal, and we get 1.0763. To take the cotangent of 14 degrees, 29 minutes, 36 seconds, we take the tangent of that angle, remembering to use our second angle key in order to get the degrees, minutes, and seconds, again, is alpha plus. When we do that, you should get 3.8686. To take the cosecant of 149 degrees, 50 seconds, we have to first take the sine of that angle and then take the reciprocal. As a note, when you put this into your calculator, you must put in 149 degrees, 0 minutes, 50 seconds. If you just put in the seconds, you will get an error. Throughout your study of mathematics, we have spent great deals of time learning processes. That is, starting with some number and doing something with it and ending up with another number. And after we master a process, we then learn the opposite process. This opposite process is sometimes called the inverse process. So, we start with x and apply some process to get y. If we then apply the inverse process to y, we then get back to x. For instance, addition and subtraction are inverse processes to each other. If we start with some number x and add 123, for example, we would get y. If we then take y and subtract 123, we know we get back to x. It doesn't matter what x is and what y is. This relationship is true. The same is true with multiplication and division. If we start with some number x and multiply it by 17 to get y, we know that if we then take y and divide it by 17, we will end up getting exactly x. Again, it makes no difference what x and y are. Square rooting is the inverse process to squaring, but with one small caveat. If we start with some value of x and square it, we get k. However, if we then take the square root of k, we get the absolute value of x, because square root must be a positive number. So if x were negative and then we squared it, we would get a positive. When we then take the square root, we then go back to the positive, not the negative. So squaring and square rooting are inverse processes when our value of x is greater than or equal to 0. So on your calculator, if you take the sine of 48 degrees, 47 minutes, 24 seconds, we get 0.7523. Now, if we take the inverse sine, which is second sine of 0.7523, we end up with 48.7900. We can then change that to degrees, minutes, seconds, and we get 48 degrees, 47 minutes, 24.021 seconds. Notice it's not exactly 48 degrees, 47 minutes, 24 seconds, which is what we started with, because there were extra decimal places beyond 0.7523, which we did not include. However, we have to be careful. Just like the issue we saw with squaring and square rooting, the same type of thing can happen with inverse trig. For instance, if we take the tangent of 225 degrees, a special angle, we know that we will end up with 1. However, if we take the inverse tangent of 1, we don't go back to 225, we go back to 45 degrees. Why does this happen? Because there are many angles whose tangent is 1. Not only 45 and 225 degrees, but any angle coterminal with 45 or 225. So which one does the calculator select? It usually will select the angle that is closest to the origin, in this case 45 degrees. In the information below, we have the basic trig function, inverse trig function relationship. We give the limitations of these statements to the right, but for right now we want you to concentrate on the following. If sine theta equals x, then the inverse sine of x equals theta, and it's sometimes called the arc sine of x equals theta. If cosine theta equals x, then the inverse cosine of x equals theta, sometimes called the arc cosine of x equals theta. And if tangent theta equals x, then the inverse tangent of x is equal to theta, and again, sometimes called the arc tangent of x equals theta. So on exercise 5, you are to use the calculator to find the following and leave your answer in decimal degrees. The inverse sine of 0.9099 is 65.4915 degrees. The arc cosine of 0.4231 is 64.9695 degrees, while the inverse tangent of 1.8089 is 61.0652 degrees. In exercise 6, we are also asked to find the inverse trig functions, but now leave our answers in degrees, minutes, and to the nearest second. So the inverse cosine of 0.4998 is 60 degrees, 0 minutes, 48 seconds. The inverse sine of 0.0809 is 4 degrees, 38 minutes, 25 seconds. And the arc tangent of negative 4.002 is negative 75 degrees, 58 minutes, 14 seconds. We know that tangent is negative in the second and fourth quadrant, but notice that our answer is given in the fourth quadrant as a negative angle because that is closer to 0 degrees than a second quadrant angle. Finding the inverse cosecant, the inverse secant, or the inverse cotangent of a number is a multi-step process, and the steps must be performed in exactly the right order. For instance, let's find the inverse cosecant of 2.3552. There is no inverse cosecant button, but there is an inverse sine button. So the first thing we have to do is take the reciprocal of 2.3552. So 1 divided by 2.3552 is 0.4246. Now we can take the inverse sine of that number, and we use inverse sine of the answer, and we get 25.1249. Changing our answers to degrees, minutes, seconds, we get 25 degrees, 7 minutes, 29.517 seconds. To confirm, let's take the cosecant of 25 degrees, 7 minutes, 29.517 seconds. Again, to do this, we have to take the sine of that angle, and we get the 0.4246. And now take the reciprocal of that, 1 divided by that answer, and we're back to the 2.3552. In exercise 7, you are to find the following inverse trig functions in decimal degrees. After you do so, it is suggested that you reverse the process to go back to the original number to check your work. So the inverse secant of 1.76 is 55.3765 degrees. The arc cotangent of 3.4221 is 16.2893 degrees, while the inverse cosecant of 1.1102 is 64.2553 degrees. Exercise 8 is just like exercise 7, but the answer should be to degrees, minutes, and the nearest second. So the arc cosecant of 3.8621 is 15 degrees, 0 minutes, 23 seconds. The inverse cotangent of 0.7501 is 53 degrees, 7 minutes, 35 seconds. And the arc secant of negative 5.8621 is 99 degrees, 49 minutes, and 9 seconds. Notice that cosine we know is negative in quadrant 2 and 3, and therefore secant will be negative in quadrant 2 and 3. And when you do this on the calculator, it will give the answer, in this case, the second quadrant, as it is closer to 0 degrees than the third quadrant. Your calculator can take trig functions and arc trig functions to extreme accuracy. However, if you input the problem into the calculator incorrectly, one of two things will happen. First, an error. Assuming you typed it in the correct syntax, the calculator is telling you that it cannot perform the operation. And this is actually good news for you. For instance, if you do a problem that you believe requires taking the inverse cosine of 1.4231, the calculator will give you a domain error because we know that the cosine of any angle cannot be greater than 1. Hopefully, you would be smart enough to realize what is happening. The logic telling you to calculate the inverse cosine of 1.4231 is faulty. You then have to go back and check your work and thinking. But second, if you input the problem incorrectly into the calculator, and the calculator can actually perform the operation, you will get an answer and you will believe it. For instance, suppose you wanted to find the inverse cotangent of 3.5. The way to do this is shown on the screen. We cannot take directly the inverse cotangent, but we can take the inverse tangent. So we take 1 divided by 3.5 and get 0.2857. Now we can take the inverse tangent of that answer, getting 15.9454 degrees. But students who do not have the calculator techniques down might know that a reciprocal is needed and then do these steps. They first take the inverse tangent of 3.5, getting 74.0546, and then take the reciprocal of that answer, and they get 0.0135. So they write down their answer of 0.0135 degrees, and they never really know they're wrong. They believe the calculator. So that is why it is vital that you learn these steps now and learn them well. Sometimes even the slightest loss of concentration can cause a problem. If you were asked to find the sine of 30 degrees plus the sine of 90 degrees, you shouldn't even need a calculator, as these are special angles and the sine of 30 degrees is 1/2 and the sine of 90 degrees is 1, and your answer is 1.5, which is confirmed by the calculator. However, if you input this quickly, you may forget to close the parentheses after the 30. And if you type in sine of 30 plus sine of 90, then you are really calculating the sine of 31 degrees, which is 0.5150. And again, as I said, you will believe whatever the calculator says. So please be very, very careful when you input information into the calculator. Prove to yourself that sine and inverse sine are indeed inverses by taking the sine of an angle and then immediately taking the inverse sine of that answer, or perhaps reverse the process. In both cases, you should end up with the value you started with. Note, though, that you must use the ANS answer key on your calculator to achieve this effect. If you type in the value, and you will not necessarily get the number you started with because of round-off error. So this is a good way to determine whether you truly understand how to take trig functions and inverse trig functions using the calculator. So we take the sine of 85 degrees and we get to 4 decimal places 0.9962. If we then take the inverse sine of that answer, we come back to 85 degrees. But notice that if we type in the inverse sine of 0.9962, we don't get exactly 85, we get 85.0035. That's because the sine of 85 degrees is not exactly 0.9962. It is that number accurate to 4 decimal places. So it could be slightly less or slightly more. So when we type in the inverse sine of 0.9962, we lose any accuracy. And that's why we don't get 85.0035. So you should get used to using the ANS key, answer key, on your calculator when you use a calculation in a further calculation. If we know 2 pieces of information about a right triangle, we can solve that triangle. That is, we can find all the information about that triangle. For this section, we'll make some generalizations, that the triangle will be labeled triangle ABC, where the side opposite angle A is labeled little a, the side opposite angle B is labeled little b, and the right angle will always be angle C, and the hypotenuse is labeled little c. We can solve right triangles if we are given one of 4 situations: an angle and the hypotenuse, an angle and a leg and the hypotenuse, and 2 legs. The formulas we will need will be the trig functions and the Pythagorean theorem, a squared plus b squared equals c squared. And obviously we will need our calculators. We should always start by drawing a picture of the given information. It does not have to be to scale, but the triangle should be somewhat close. Any work that you do should be shown and answers placed in the appropriate positions. We will assume that accuracy in sides is 2 decimal places and angles are to be in decimal degrees unless otherwise stated. So if an angle is given in degree, minute, and second format, then assume that the other angle should also be in that format. To best understand the process, expect problems to be given in this format. I call it the family method, where you show the A family, the B family, and the C family, where angle C is always equal to 90 degrees. You should then draw the picture and do the work on the right side. While the calculator does the number crunching, you must show how you're calculating your answers. I also like to box my answers so it is clear when I look at the problem later what was originally given and what was found. When we solve a right triangle, we prefer to use given information rather than values we just found. If there is a mistake in information found, then any subsequent calculation using that information will also be wrong. Solving right triangles can always be accomplished by using just the given information. But if you choose to use a value that has been found on the calculator, then it is best to save that value as a variable, so you will always have as much accuracy as necessary. While checking your work is not necessary, doing so ensures that you have the correct answer, and it only takes a few seconds. If you did not use the Pythagorean theorem in your solution, then you can check the accuracy of the sides by using it. And while the hypotenuse must be the largest side, the smallest side must always be opposite the smallest angle. However, the legs of the right triangle will not be proportional to the angle. For instance, in a 30, 60, 90 triangle, the ratio of 60 degrees to 30 degrees is 2 to 1, but the ratio of sides is the square root of 3 to 1. Still, the larger the discrepancy in angles, usually the larger the discrepancy in sides. Exercise 9 is an example of an angle and a hypotenuse. We are told that angle A is 21 degrees, and angle C, of course, is 90 degrees, and little c is equal to 14. We wish to find angle B, little a, and little b. We draw the picture somewhat to scale. To solve this problem, we first find angle B, which is 90 minus 21, and that is 69 degrees. Next, we will look for little a. Relative to angle A, little a is the opposite, and we also know the hypotenuse. Opposite over hypotenuse makes us think of sine. So we write the relationship, sine of 21 is equal to a over 14, and therefore a is equal to 14 sine of 21 degrees, which is 5.02. To find little b, relative to angle A, little b is the adjacent, and we know the hypotenuse. Adjacent over hypotenuse is cosine. So we write the relationship, cosine of 21 degrees is b over 14, therefore b is equal to 14 cosine of 21, and that's equal to 13.07. So our final answer is b is 69 degrees, little a is 5.02, and little b is 13.07. To check this, we confirm that the smallest angle A is opposite the smallest side A. And when we look at the Pythagorean theorem, we square 5.02 plus 13.07 squared, and we get almost 14 squared. It's not exactly 14 squared, which is 196, but it is close. The reason that is not exact is that these answers have been rounded to 2 decimal places, and therefore we lose the accuracy. 10 is an example of an angle and a leg. We are given angle A is 77.2 degrees, angle C is of course 90 degrees, and now we have little a, which is 29.5. We draw the picture somewhat to scale. To solve, we first go for angle B, subtracting 90 minus 77.2 to get 12.8 degrees. We can use either angle A or angle B. We're confident of angle B being correct. Relative to angle B, we want to find little b, which is the opposite, and we know little a, which is the adjacent. Opposite over adjacent gives to mind tangent, and therefore our statement is tangent 12.8 degrees is equal to b over 29.5, and therefore b is 29.5 tangent 12.8 degrees, and we get 6.70. Now we need the hypotenuse, c. In this case, I choose to work with angle A because we know the opposite and we want the hypotenuse. Therefore, we set up the sine of 77.2 is 29.5 over c. Now, when we cross multiply, we get c is 29.5 divided by sine of 77.2, and that gives us 30.25. There is more than one way to solve these problems. For instance, just looking at C, we could have set up the relationship that the cosine of 12.8 degrees is 29.5 over C, and therefore C is 29.5 over the cosine of 12.8 degrees. We'd also get 30.25. We could also set up the relationship that the cosecant of 77.2 is c over 29.5, and c is 29.5 cosecant of 77.2 degrees. Or The secant of 12.8 degrees is c over 29.5, and c is 29.5 secant of 12.8 degrees. We generally prefer not to use cosecant, secant, and cotangent because we do not have keys for them on the calculator, and we have to do the one extra step to calculate them. But it is certainly okay to use these functions if you wish. We could also use the Pythagorean theorem, saying that c is equal to the square root of 29.5 squared plus 6.70 squared. Of course, this violates our general principle that we shouldn't use given information that we just found, but if the information is correct, the answer will be correct. So the final answer is that angle B is 12.8 degrees, little b is 6.70, little c is 30.25. To check it, notice that the smallest angle B is opposite the smallest side B, and using the Pythagorean theorem, we get 29.5 squared plus 6.70 squared is 915.14, and 30.25 squared is 915.0625. The difference is simply round-off error. 11 is similar to 10 in that we have an angle and a leg. However, in this case, angle A is given in degrees, minutes, and seconds, and little a has units of millimeters. That doesn't change how we do the problem, though. We still make a picture relative to scale to give an idea what kind of answers we should expect. This problem is done similar to example 10. We first do the subtraction. B is equal to 90 degrees minus 38 degrees, 12 minutes, 44 seconds to get 51 degrees, 47 minutes, and 16 seconds. We can do this on the calculator as shown, realizing that once we do the subtraction, our answer is in decimal degrees. We need to change it to degrees, minutes, seconds. There's many ways to set the problem up, but working with angle B, we want to find little b and we know little a, and that represents the tangent function. So we can immediately say that b is equal to 102.35 tangent to 51 degrees, 47 minutes, 16 seconds. We can say the step by saying that, and therefore our answer is 130.01. The same thing is true with working with the angle A. We want to find the hypotenuse, and we know little a, and that is going to use the sine function. And since sine of 38 degrees, 12 minutes, 44 seconds is 102.35 over c, we could write immediately that c is equal to 102.35 over sine 38, 12, 44, and we get 165.46. Note that we do not put our units, millimeters, into the work. We only use them in the final answer. So our final answer is angle B is 51.4716, while little b is 130.01 millimeters, and little c is 165.46 millimeters. To check it again, the smallest angle is opposite the smallest side. And by using the Pythagorean theorem, we take a look at 102.35 squared plus 130.01 squared, and we get 27,378.12. And when we look at 165.46 squared, we get 27,377.01. There's a little discrepancy, but again, it's round-off errors. Example 12 is slightly different. We have a leg and the hypotenuse. This means other than the 90 degrees, we do not have any angles. The picture is drawn somewhat to scale. Since we do not have the angles, we cannot use trig functions to find the missing side. However, we can use the Pythagorean theorem, and therefore b is equal to the square root of 13 squared minus 8 squared, or 10.25. To find one of the angles, we'll choose angle A. We concentrate on the two known sides, which are 8 and 13, the opposite and the hypotenuse. So sine of A is equal to 8 over 13, which means that A is the inverse sine of 8 over 13. And that gives us 37.98 degrees. We cannot find B unless we use angle A. So we have B is equal to 90.37.98, and angle B is equal to 52.02 degrees. So our final answer is that A is 37.98 degrees, B is 52.02 degrees, and little b is equal to 10.25. To check, again, we find that the smallest angle is A, and that is up against the smallest side. And it doesn't make sense to use the Pythagorean theorem to check the sizes of little a, b, and c, because we use the Pythagorean theorem to find b. So we will work with one of the angles and take a look at the trig function. We'll use angle A and check that tangent of 37.98 is equal to opposite over adjacent 8 over 10.25. And we find that other than a slight rounding error, the two values are exact. Our last example is a leg and a leg, and we are asked to find our angles in degrees, minutes, seconds. We have little a is 2 feet, little b is equal to 15 inches. Obviously, there's a trap here, as the units are not the same. We must choose whether to work in inches or feet. There's no one right way to do it. It is easier probably to work in inches, as everything will be integers. So little a is 24 inches, and that is shown by the picture drawn somewhat to scale. To solve, we again use the Pythagorean theorem, getting c is equal to the square root of 24 squared plus 15 squared, which is 28.30. To solve for an angle, we'll choose one. We'll talk about angle A, and relative to A, we know the opposite and adjacent. So the tangent of A is equal to 24 over 15, and therefore A is equal to the inverse tangent of 24 over 15. And getting our answer to degrees, minutes, seconds, we get 57 degrees, 59 minutes, and 41 seconds. We can find B by subtracting that from 90 degrees, getting 32 degrees, 0 minutes, 19 seconds. So our final answer is that angle A is 57 degrees, 59 minutes, 41 seconds. Angle B is 32 degrees, 0 minutes, 19 seconds. And little c is 28.30 inches. Important to put the units. To check, we'll work with angle B and realize that that is the smallest angle and it's opposite the smallest side. And working with angle B, we look at what we know, and we know the opposite, and we have found the hypotenuse, and therefore we will set up the relationship that sine of 32 degrees, 0 minutes, 19 seconds turns out to be 0.5300, and 15 over 28.30 is also 0.5300. Solving individual right triangles is straightforward, but sometimes you have some more complex problems where you have to use one piece of information to find another piece of information. In example 14, we have a figure where angle A is 25 degrees, angle B is 40 degrees, BC is equal to 12, and we're asked to find AB. The first thing we do is place our angles and sides onto the picture so we get some sense of what we're looking at. We realize that we are trying to find AB, and AB is not part of a right triangle, which means that you cannot find it directly using trig. We're going to need a multi-step approach to find it. Even though we are not asked to find CD, finding its value is the key to doing this problem, because CD is common to triangles BCD and ACD. So we start by finding CD by using the relationship that tangent of 40 degrees is CD over 12. And therefore CD is 12 tangent 40, and that makes CD is equal to 10.07. We then work with the 25 degrees and realize that tangent of 25 degrees is CD over AC. But now we know CD, which is 10.07, and we're over AC. So therefore AC is equal to 10.07 divided by the tangent of 25 degrees, and that makes AC equal to 21.59. And therefore AB must be 21.59 minus 12, which is 9.59. Problem 15 tweaks problem 14 just slightly. We know that angle A and angle B remain the same, 25 degrees and 40 degrees. But now AB is equal to 12, and we are asked to find CD. This makes the problem much more difficult. We start by putting the information onto the picture. We realize that we are trying to find CD, and in triangle BCD, we know all the angles, but we know no sides. And that makes it impossible to find any of the sides. In triangle ACD, we know the angle and part of a side. Is that enough to help us find CD? We start by writing some trig relationships. This is a problem that works with the legs of the triangles, and the hypotenuse really doesn't come into it. So we'll be using the tangent function. The tangent of 25 is opposite over adjacent, CD over AC, and therefore CD is equal to AC tangent 25. We do the same with 40 degrees. Tangent of 40 degrees equals CD over BC, and therefore CD is equal to BC tangent 40. Since both of these expressions are equal to CD, we can then write that AC tangent 25 is equal to BC tangent 40. Notice that we do not find the tangent 25 degrees and tangent 40 degrees. Doing so is going to involve us with messy decimals. We prefer to do all of these calculations at the very end of the problem. The key to this problem is realizing that AC is equal to AB plus BC. So we can break up AC into 12 plus BC. So in our last statement, we can write 12 tangent 25 degrees plus BC tangent 25 degrees is equal to BC tangent 40 degrees. Looking at that, we realize that we know all the information except BC. That's the only unknown. So we will factor it out and write 12 tangent 25 degrees is equal to BC times the quantity for tangent 40 degrees minus tangent 25 degrees. And therefore, we can write BC is equal to 12 tangent 25 over tangent 40 minus tangent 25. At this point, we can now use the calculator and get our answer to 2 decimal places, and BC is equal to 15.01. But we are not trying to find BC, we're trying to find CD. But now we have the base. of triangle BCD, and therefore CD is simply 15.01 tangent 40 degrees, and that makes CD equal to 12.59. Later in the year, we will learn to work with triangles that are not right triangles, and we will have a completely different approach to this problem, which will make it slightly easier. In example 16, let's do the exact same problems, but rather than know the specific values of angle A, angle B, and AB, let us write our formula for CD in general terms of angle A, angle B, and line segment AB. We start the problem the same way. We take the tangent of A, writing it as CD over AC, and therefore CD is equal to AC tangent A. We write the same type of relationship with angle B. The tangent B equals CD over BC, and therefore CD equals BC tangent B. And therefore we can equate the two, writing AC tangent A equals BC tangent B. The key to the problem is breaking up AC into AB plus BC. So we have AB tangent A plus BC tangent A equals BC tangent B. We can then bring the BC tangent A to the right and factor, getting AB tangent A equals BC times the quantity tangent B minus tangent A. And therefore BC equals AB tangent A over tangent B minus tangent A. But we're trying to find CD. From our second statement above, we know that CD is equal to BC tangent B. So we end up with the statement that CD is equal to AB tangent A tangent B all over tangent B minus tangent A. You may want to go back to exercise 15 and plug in the values of A being 25, B equals 40, and AB is equal to 12 to show that you get the same answer. Now that we have gotten through solving of right triangles, we are now ready for applications. There are multiple applications for trigonometry, and we will study them in video 03B.